All right, welcome everybody. This is a lesson 1 of the acid-base unit. We're just going to do really brief here. There's not much to talk about, but we're going to be talking about acids and bases, some of the common acids, common bases. A lot of this you'll just have to review from the booklet yourself. So acids and bases in our class are going to be those that donate a proton or accept a proton. So acids, proton donors, and bases are proton acceptors, and we'll see how this works. We can think about these acids as being also a hydronium producer, because when you're doing a reaction in water and you add H plus into a water, you'll instantly get the creation of H3O plus, or hydronium. And this hydronium is actually the most common form for a proton in water. They've actually done a lot of experiments, and they've never really successfully captured a single proton existing by itself in water. Remember that a proton is really, really small. So if you look here at this little picture here I've drawn of an atom, here's your atom, right? And this is our electron density up here. So there's an electron somewhere in that circle. And there's a little tiny spot in the middle. That's our proton. And if we could zoom in, we should probably, this should actually be a little tiny plus symbol. So, it looks like a star. Okay, so it's a little tiny plus. And so this little tiny positive charge, right, on the inside here, this little tiny positive charge, if you scrape off the electron density, it's really, really tiny. So that's what we're dealing with. We're dealing with something that is ultra small, and this is why acids are dangerous, really, is that these protons can get into all sorts of mischief. And so we can have something like DNA. DNA is held together by protons. So if you do something like add a base to DNA, which is a very common tactic for denaturing DNA, is to use a base. Well, bases have hydroxides, and hydroxides eat up protons like their dinner. And then the DNA strand will actually fall apart. And all sorts of other examples. So a lot of our body's chemistry is controlled by protons. A proton in a certain protein will make it function. If there's no proton, then we'll have troubles. So every acid produces protons and something else. There's usually some other component. They're essentially salts, but they're special hydrogen salts. Now there are the occasional acid that will increase the amount of protons in the solution without having protons itself. It might be able to do this by scraping a hydroxide off something and leaving a proton behind. But we'll deal with that in a little bit. Protons and hydroxides are particularly dangerous in chemistry because they can react with many types of bonds, causing many different chemical changes. So here's an example. You've got an acid here and an alcohol. This is one we would have done in an organic unit if you did Chem 30. And the product is an ester. And this is one of the chemical reactions we use to create smells. And these reactions can even happen inside the body to produce scents in flowers, or, well, not in our bodies, in plant bodies. So hydroxides, on the other hand, or bases, so here's our base. These bases, they tend to produce hydroxide because hydroxide will consume protons. So hydroxides, if we think about a hydroxide, if we add it to a solution, let's use our hydronium because that's a little bit more accurate. So if you have something that increases the amount of hydroxide in solution, then this will force the reaction towards the formation of water, actually 2 waters. So that's why bases are dangerous. We can really think about them as changing the amount of protons, and it's concentration of protons that really is important. So yeah, and so, often they will be thought of as producing hydroxides. Anything that produces a hydroxide is a base. Also, anything that consumes a proton is a base. So here's some properties. Acids taste sour. This is something we always say. That's because a lot of the food we eat is controlled by acid. I believe there's even a cookbook called something like acid, fat, something, something, heat. And so it talks about the components of cooking. One of the four components of cooking is acid and how much acid you have. Acids are corrosive to metals, so this is why we want to keep them away from metallic things. You can work with them in plastic or glass, but working them in a metal container is dangerous. You'll get some corrosion. Acids are used in batteries, and one of the ways that a lead acid battery breaks down is that the metal on the inside of the battery starts to corrode under the acidic conditions, or it corrodes too much that you have to replace it. Excuse me. All right. All the acids end in ic if they were originally in ide. So if it was something you would have called an ide, say sulfide, then it becomes a sulfic. Sulfuric comes from hydrogen sulfate. Sulfates also become ic. Sorry, I'm thinking about chlorides. Yes, hydrogen chlorides become hydrochloric. So here's our ic. That indicates that it's an acid. This is the strange part about acids and bases, is that acids have all these rules for naming. So sulfuric acid, hydrochloric acid, nitric acid, acetic acid. There's the nitrous acid, which comes from nitrite. This is nitrite. And this is sulfite, SO3, this is sulfite. So sulfite becomes sulfurous, and phosphoric, and hypochlorous, so from chlorite. These are all acids. We use them all over the place. You can read those little definitions about where they've been used, and we're going to carry on. Now many of these acids are monoprotic. That means that they produce only a single proton, whereas a polyprotic acid is one that produces two protons. These can become tricky because the second proton is usually harder to remove, and sometimes they even have three protons, and each proton becomes more difficult to remove, which causes the formations of equilibria between those later protons. So we'll work with those later. Bases are anything with a pH above 7. In nature, we don't eat bases very often because our body is really built for acidic systems. Think about your stomach. Your stomach is filled with hydrochloric acid, which is pH of 2. If you were to eat something very basic, you'd have a very intense reaction in your stomach. So even something like milk, if you add in the lactic acid in milk, you actually end up with something that's around a pH of 6.8, I believe. Very close to 7. All right. Most of these bases produce hydroxides. So we have sodium hydroxide, potassium hydroxide. All of these are bases. Ammonia is probably the only peculiar one. Ammonia is a base because of that earlier reaction we showed where it actually consumes a proton. So the ammonia reduces proton concentration because when it reacts with a base, you'll get the production of NH4, which is an acid, and water. And so we can see that the amount of proton has gone down because it is now part of the ammonia, forming ammonium. And so monohydroxic acids, these are any of the hydroxide based acids that only produce a single hydroxide. All of the first column alkali metals would count. Polyhydroxides have metals that are charged, so magnesium or strontium, something like that. The reaction of an acid and a base always causes a neutralization, The proton acceptor accepts the donated proton from the acid, and so this combination produces water. The combination of the other parts of the base and the acid are opposite in charge, so they can form a salt. So let's look at this hydrochloric acid. Think about this in the ion form. We have a sodium plus and a hydroxide minus. So we can think about it that, in this case, sodium chloride is very, very soluble, so it's not very exciting, but you do always produce a negative counter ion from an acid and a positive counter ion from the bases, at least those that are hydroxide and proton-based acids, bases. And so those counter ions can even have their own equilibrium in some cases. You could even have something like a lead hydroxide mixed with a hydrochloric acid, and you could be forming lead chloride. That's a very exciting reaction to have happen. All right. But pretty complicated. It gets pretty tricky to calculate those sorts of things. So here we show this sort of broken down a little bit more. We break it down into its full ionic form. We remember that sodium chloride has a very high solubility, so you can see here that I actually removed the sodium and the chlorine from both sides, and in that removal I form a net ionic equation down here. Here's my net, and you can see the net ionic equation again is just a proton plus a hydroxide gives us water. So here's a full set of equations. We have our full equation of potassium hydroxide, KOH, and sulfuric acid, H2SO4. Both are a strong base, strong acid. They will react to form water and form this salt. If I go and look at my solubility rules from the last unit, I'll realize that this K2SO4 is aqueous. So we can write out the salts. We can write out the ionic equation here. So here's our ionic, and then we can write out the net equation as we cancel out those ions that are spectators. All right, acetic acid and sodium hydroxide, very similar. Nothing too exciting here. This one's even easier because both acids produce a single. The acid produces a single proton, and the hydroxide produces a single hydroxide. I'll have a small comment here about acetic acid. Acetic acid, in the traditional way of writing it, you typically write COOH, and this is written specifically to emphasize that hydrogen is acidic. So we can write this out. It's actually, the compound looks something like this, and there are a double bond to the oxygen, and then a single bond, and then a bond to the OH. And this hydrogen here sitting on the edge, it has almost no electron density because you have a very strongly electronegative oxygen, a really strong electronegative oxygen here. So these pull all the electron density in this area away from the hydrogen, leaving this hydrogen very bare and exposed and having a very partial positive charge with a strong partial negative charge on the oxygen. So that hydrogen is ready to fall off, and as soon as it finds somebody else with a little bit more attraction, it's going to leave and go join them. And that might even just be a water nearby. So even a water that's nearby has a little bit more electron density for it, and so the electron density on this oxygen can actually stretch out and steal the hydrogen away. And that's essentially how that acidic reaction happens. So here's sulfuric acid and potassium hydroxide, similar process. We have the issue of the sulfuric acid has a H2, so we have to worry about that. And then we have some practice. So I'll just point out that this first practice question is calcium hydroxide. Calcium has a 2+ charge, so it is a diprotic acid. And I'll leave it there for you to